We are now going to look at the chain rule, which is a powerful technique that we use to differentiate composite functions. Without fully understanding what composite functions are and the notation of them, the chain rule will appear complicated and unclear in its application. Once you understand composite functions, the chain rule is simple, and I really can't emphasize this enough. I will run through the general method alongside an example, since the language of the chain rule can be confusing. Let's say we have a composite function y is equal to fg of x, and we want to find dy dx. The example we will use will be y is equal to the sine of 4x squared. The first step is to identify what the functions f and g of x are by themselves. In this case, the outer function f is sine, whose argument has been replaced with the function g of x is equal to 4x squared. We then wish to make a substitution on the innermost function to avoid too much messy notation, and so instead of g of x, we will just write u. So u is equal to 4x squared, and y is equal to f of u, which is equal to sine u. So far we haven't done anything other than change the way it looks. Now we exploit a handy trick. We have the innermost function u in terms of x, and we can differentiate u with respect to x to get du dx. We have the outer function y in terms of u, and we can differentiate y with respect to u to get dy du. And for us, dy du is just equal to cos u. For both these differentiations, I can just use the table of standard differentials from the second video. Here's the magic part. When we multiply together dy du and du dx, we see that the du's cancel, and we are left with dy dx. We do this for our example, and we notice it looks a bit strange since there are still u's in it. But that's no problem, since we just replace the u with what we defined it to be, in our case 4x squared. This can easily be extended to higher level composite functions, such as y is equal to f, g, h of x. For our example this time, we will use y is equal to the cos of e to the power of 2x, and we want to find dy dx. We identify the functions h of x, g, and f by themselves, looking for the standard functions which we know how to differentiate. H of x is going to equal 2x, the function g is e to the power of, and the function f is just cos. We then call the innermost function h of x equal to u. So now we have y is equal to f g of u, or y is equal to the cos of e to the power of u in our case. We then repeat the step of renaming the innermost function, which is now g of u. In our case, g of u is equal to e to the power of u, and we will call this v. So we now have y is equal to f of v, which for us is cos of v. We differentiate u with respect to x to get du dx, v with respect to u to get dv du, and y with respect to v to get dy dv. When we multiply these together, the du's and the dv's cancel, leaving us again with dy dx. Doing this leaves us with negative 2e to the power of u times sine v, and we replace all the u's and v's, which will eventually result in negative 2e to the power of 2x times the sine of e to the power of 2x. Don't expect to fully understand this first time around, But please believe me, if you persevere with this technique and understanding it in terms of composite functions, you will eventually be solving chain rule problems very quickly and with very few errors and confusion.